bear with me, I'm afraid. Okay, well, there we go. Forth as a Micromouse tool. Now, I'm going to talk about the use of Forth as the ideal language and system for developing Micromouse robots. As we go, ask the questions, because otherwise people are going to lose track, and I'm going to lose track as well. I haven't presented to this audience before, so I'm likely to miss explanations of some things. Some of you may have watched the video link I put up last time and have some idea what I'm talking about. For the others, Micromouse is a group of competitions for small, that's less than 250mm cube, 125mm cube for half size, autonomous robots. The classic maze solving event has been going for at least 45 years, but I only got involved in 1996. Some of you may remember a paper I gave to Euroforth 97 on maze solving. Is everybody happy with what Micromouse is? I can show you a few seconds of video if it'll let me.
Anybody that's not happy, speak up now.
Go ahead, and I would be interested in hearing briefly what it is.
Okay, well, I'll do my best to show this video. It might work, it might not. Sharing is always the challenge, switching between things, but I might get there in the end.
Brad, is there a switch for sharing when you're going to show a video?
There is. When you hit share, you want to make sure that you check the button for optimize for video sharing right before you share that window. So on the right-hand side, there'll be a checkbox for optimize for video sharing, and also share sound so that we get the audio.
Well, everything seems to work except I can't find the thing I'm trying to share, which appears on my screen beautifully. Try that again. There it is. Okay. Right, so this is a famous video from Veritasium. I'm just going to show you the first few seconds because it should give you some idea what we're trying to achieve.
This tiny robot mouse can finish this maze in just 6 seconds. Every year around the world, people compete in the oldest robotics race.
So that's what I'm trying to do. It's not as easy as it looks. Let's get back to
it. Looks hard.
Yes, it is. Sorry, I'm just fighting the Zoom thing again. I will get there in the end, I think. That's where I want to do. And share again. It might get more smooth as I get further into it. Okay, so that's what we're trying to do. Today I'm going to concentrate on why Forth is so good in this application, and I'll show my latest maze solving algorithm. As a bit of a background, I'm a retired electronic engineer. I've been using Forth professionally and as a hobbyist since about 1982. I mostly use the MPE versions. I have a gang of teenagers, currently 4, that build Micromouse in my shack on Tuesday evenings. I've been doing this for the last 25 years. I find Forth a good language for them. In particular, it encourages an engineering approach to software. So these are 3 of my mice. These are giving you some idea of the different competitions that there are and the classes there are. Now, the one on the left is a classic sized wall follower stroke maze solver. It can do both with a few extra sensors added. The one in the middle is a half-size maze solver, and the one on the right is a half-size line follower. The original 16 by 16 maze has 2 classes. Wall following is as an entry level and solving for the experts. This is the classic event and is the target for most new Micromouses. So somebody comes along to a competition, they see all these wonderful things whizzing about, think I could do that, and they tend to try for the solver as their first attempt. I wouldn't recommend it. The line follower is much easier. There are half-size versions for those two events. In Japan, they run on a 32 by 32 maze for the half-size. In the UK, we've stayed at 16 by 16 so far. A lot of the UK people have designs in progress, but there are only a couple of successful solvers as yet. The line following events are what you would expect. You have to follow a line. The UK has moved exclusively to half size because this enables you to have small courses that are much easier to transport and so on, and still make them reasonably complex. There's a new event that we're going to be trialing this year. We've done once an exhibition at a MegaCon. I think some of you might know that as Comic Con. Lots of people dressed up in fancy dress. I felt that the odd one out, dressed as a retired electronic engineer compared to the Hulk and Batman and all the rest of these people. But they wanted something a bit more exciting. So we're developing a pursuit event where two robots chase one another around a course, a bit like cycle pursuit racing. So that's something that's in the pipeline. For all the events, there are senior and junior classes. That's junior is under 18. And depressingly for the adults, it's reasonably common for the juniors to beat the grown-ups in line following and wall following. There are very few successful junior solvers because it takes so long to develop a successful mouse. Now, this is the sort of thing that we want our mice to be able to do. These are the sort of thing that the very best Japanese mice are currently achieving. In the UK, we're not so good. The UK champion currently achieves about 3G acceleration. I'm happy to get close to 1G, but I aspire to get quicker. It would be ridiculous to choose a software platform that was incapable of doing that. Just to put it all into perspective, Formula One cars achieve about 3G, and fighter pilots black out at about 9G. Now, just to give you some scaling numbers, the mouse must be able to detect the posts of the maze whilst travelling past them at full speed. Full size, these are 12 millimeters wide, half size 6 millimeters wide. The markers for line following are 10 millimeters wide. At 1 meter per second, you have just 6 milliseconds to detect a half size post. At 5 meters per second, you have just over a millisecond. You should design your system so that you sample walls better than once per millisecond and probably twice that speed. Micromouses get obsessive about weight. Shaving 1 gram off a 40-gram half-size mouse is well worth doing. 0.6 millimeter PCBs are lighter than 0.8 millimeter PCBs. 32-pin microcontrollers are smaller and lighter than 48-pin versions. Do I really need lots of memory in a bigger chip? If I can cut power consumption by 10%, I can use a smaller and hence lighter battery. So it's not obvious what the limiting factors are. Many particular problems can be solved in a number of ways. For example, sensor issues can be solved by optical methods. I've been known to use mirrors. Mechanical methods point them in a different direction, or in software. These can have massive effects. For example, my wall follower has a critical sensor direction that interacts with the current speed and the PD control constants in the mouse positioning controller. Change any of these and it goes slower. It's best for the sensor position not to be susceptible to movement when the mouse inevitably hits a wall at high speed. Sometimes they crash into multiple pieces. The UK champion was competing a few years back at our local competition about 3 weeks before Japan, and his mouse hit the corner of a wall and ended up in about 8 pieces. It's quite a big job to reconstruct it in time. Every part of the mouse is critical. Fit a lighter battery and you screw the weight distribution. My current line follower has lead weights above the wheels to improve traction. If you fit lighter 3mm LEDs instead of 5mm LEDs in the wall sensors, you screw the optical spot size. Fit slick tyres and you pick up too much dust and your grip drops off the longer you have been on the course. What you want to be able to do is change everything very rapidly so that you can achieve the fastest possible development cycle. 3D printers help. Fast turnaround PCB manufacturer helps. Rapid delivery from suppliers helps. Most importantly, fast software iterations are vital. Small is beautiful, except for line followers where wide ones can track further from the center of the line. Weight is not critical, but power to weight ratio is. Even more critical is moment of inertia about the center of the wheel track, because the more compact you can make the mouse, the faster it can change its rate of turn going into and coming out of corners. Stiffness can matter. Nobody uses suspension yet, but it's only a matter of time. Two wheels, like a wheelchair, is obvious, but front to back weight transfer is a limiting factor. Four wheels has been used very successfully, but it causes unpredictable tyre slippage in turns. With a four-wheel mouse, two pairs of wheels, it's pretty obvious that only three of them are going to be in contact with the floor at any time. Depending which three are in contact with the floor will depend where the turning centre is and hence how much turn you get. So if you've got a four-wheel mouse, you're going to need a gyro so you know when you've turned through 90 degrees. Four wheels with a steerable axle is another option. It's quite often used in the line followers, but it's very tricky to get a fast response because you've got all the weight of these wheels to turn. At least one mouse uses six wheels at different heights. It balances on the center wheels during turns and settles onto four wheels during acceleration and braking. So it's either tipping backwards during acceleration onto those four wheels or tipping forwards under braking onto those four wheels. And hopefully in the turns it's balanced and it's a two-wheel mouse. Three or four wheels that are independently steered and driven has been done a few times. It's quite amusing, but unlikely to be fast. Nearly everyone uses direct PWM drive to the motors with control via odometry. I use analog drive to the motors with a back EMF sensing compensation for the motor resistance. Mine is comparatively complex, but has a bandwidth of 10 kilohertz or more. Odometry-based control cannot do anything until the motor has moved to the next count. So until you get a pulse from the odometers, you don't know what's going on. In practice, my system does very well at following events, but may not be ideal for solving events. Time will tell. Most mice use reflected light sensors for detecting wall or line position. The amount of detected reflected light is, in principle, proportional to the inverse square of the distance. The presence of bright ambient light, sunlight, makes life difficult. What we do is that the system turns a bright LED on, takes a reading from the photosensor, turns the LED off, takes another reading from the photosensor, and subtracts the second one from the first. So you're subtracting the ambient light from the reading. But you still need a sufficient dynamic range in your sensor to cope with the worst possible sunlight. And some venues, at some times of year, you get low sunlight through the windows. And while the judges will do their very best to put curtains and things to block off the sunlight, it doesn't always happen. You need to be prepared for it. This system is very lightweight, but it's also susceptible to differences in reflectivity. So a maze at one competition, the walls might be cleaner or whiter than the walls at a different competition. So every time you go to a competition, you typically have to calibrate the sensors so that they can convert the amount of light they see to a distance more accurately. And you'll see most of the mornings, the solver people will spend an awful lot of time fiddling around in their maze trying to get their mice reliable. It's not always possible. Right, this kind of reflected light sensor can be quick. If you use fast sensors, fast ADC and good electronics, you can make a measurement in 10 microseconds or so. Poor electronic design, sadly an awful lot of people have this, can make the readings dependent on the time between readings and any variation in the execution time of the reading routine. So you've got these, how can I describe it? You turn the LED on. If the electronics is not accurate, the brightness of the LED will be dropping with time as it discharges the storage capacitor. You're using a phototransistor as the sensing element. Some people do, I use photodiodes. But the problem with the phototransistor is it takes time to respond, it's quite slow. So the actual light that the sensor can see is on a bit of a curve like that. So if you sense not on the peak, you'll get a different reading. And if you've got jitter on when you sense, that'll put jitter into your distance measurements, and that'll mess up your control system. If you can make the readings fast enough, you can increase the LED power dramatically. You obviously want as much LED power as possible to swamp sunlight and also to give you the maximum possible range. And I hit my bright LEDs with 1 amp pulses. I deal with some sensor electronics and optics. I've done a paper about it, and I'll put a link to that on the chat when I finished. There are lots of possible tricks with optics. You need small spots of light from the LEDs to make accurate measurements of wall edges, so you can make turns at the right place. Some people use lasers for this reason, but they're heavy and potentially dangerous. You need to ensure that the spot of light is visible by your sensors at all ranges. A wide field of view can be useful. This is on the sensors. You may not have enough ADC channels for your sensor array, so you might consider multiplexing one sensor between several LEDs. For example, the Raspberry Pi Pico, I think, has only got 3 usable ADC channels, so it gets a bit difficult to use that. You need to consider any direct optical path between the light source and the sensor. So the light source and the sensor might be pointing in the same direction, but there might be light flowing directly across between them, and that will affect you. So I sometimes use Tipex or black paint or bits of cardboard or anything like that to block this direct path. And you also need to think whether the sensor is shielded as far as possible from ambient light. So for all those reasons, blinds, mirrors and lenses have all been used. Don't imagine that sensors are easy to design. Now we come to the stuff that you're probably most interested in, software. So software brings it all together and can help to solve problems caused by failings in other bits. It's proper, hard, real time. As I said, any variation in the sampling times for the sensors or the odometry comes out directly as noise in the control loops. So it will affect how accurately you can control the robot. Control software has to be fast. The response time of the mouse can be limited by software sampling rates. Sub-millisecond loop times are very desirable, but good electronics may reduce that requirement. In the limit, all the hardware control could be done by electronics or an FPGA, and the software would only need to run the solving algorithm and the user interface. But I don't know of any mice that do this. Software is weightless. That's in heaviness, not in time duration. So here we are, fourth. It's hardly surprising that fourth is desirable because it was originally designed for control purposes, I believe. Speed is very important. As I've pointed out, everything about the mouse has to be fast enough to achieve the desired performance. And there's no obvious constraints on fourth, it's fast enough. A friend of mine decided that he needed to learn Python for his astronomy course. He chose a Micromouse as the vehicle, sorry about the pun, to do this. He is in a world of grief. For reasons that are unclear, his Python goes away for 7 milliseconds at a time. The current theory is that it is something to do with garbage collection brought about by the use of floating point numbers. But if you try and get posh with your software, for example, using an operating system, Linux or something, right? You quite often find that with a real-time operating system, it's still got latencies in the hundreds of microseconds, and that would make it unusable. Because Forth doesn't have anything like that built into it. Interactivity is very important. So in Forth, the interpreter runs words at full speed. It's vital. So many mouse functions are time critical. If you use a language that adds checkpoints, etc. for debug, those checkpoints had better not change the real-time performance at all. Some bits of my code have critical code timing loops. An example would be waiting for a photo sensor to settle after you turn the corresponding LED on before taking a reading. Now, I don't know in advance which bits of code will need debugging next. I don't have to recompile and download in order to exercise the next bug. A lot of people in other programming languages have to write little test routines to try things out. If I've written it, I've got it, I can test it. I sometimes use interactivity over Bluetooth while the mouse is running. So I can have a task talking to me over Bluetooth on a terminal, while the rest of the mouse is running in other tasks. So the mouse is zipping around, for example, a line follower course, and it's doing a control loop where you've got speed and a proportional control constant and a differential control constant. And via the Bluetooth, I can change those interactively. So I can turn the speed up a bit and see how much effect that has, perhaps turn up the proportionality constant, see I've made it wobble a bit, turn up the derivative and smooth out that wobble. And I can do that interactively until the mouse is just on the point where the tires would break away. You can really get that mouse to hang out on the corners. It's really impressive. There may be other ways of doing this, but Forth does it very nicely for me. Now, consistency is important. When you make small changes to the code, it should result in small changes to the execution. So the one-to-one correspondence between Forth words and executables is beautiful. I once used a C compiler where, when I took some code out, sometimes the object code got bigger, and I still haven't worked out why. With an optimizing compiler, it's entirely possible that the compiler will change a variable from a register to memory, or vice versa, as a result of something that happens in a completely separate section of code. So that makes debug of time-critical sections impossible, because you change something over here, and the bit that you've proved worked no longer works. Similarly, processors that use memory cache can be a whole world of trouble. And I really have no idea how you get on with these multi-core things where you've got multiple processors sharing the same memory. I wouldn't want to go there. Small footprint for the software helps with the choice of microcontroller. The chips with more memory tend to come in physically larger packages. As you can build a mouse with as few as 20 pins on the microcontroller, you want the option of using small controller packages. I can fit any of the mouse events in 64K of flash on a 32-bit processor. And for a following device, something that doesn't need the solver in it, 16 kilobytes on a 16-bit processor is sufficient. Multitask is pretty much ideal for Micromouse. Because of the real time constraints, any preemptive scheduler will introduce jitter into the control loops, so a cooperative one is better. Tasks don't relinquish control until they're good and ready, so task swaps in critical code don't happen. Typically, I'll have a control loop task that runs to completion without any pauses. Then it goes into a wait loop until the next timer interrupt. During this time, the other tasks can get a go. The other tasks can be the solving algorithm, any data logging, and the user interface. As long as these all pause before the next timer interrupt, everything is fine. Cooperative scheduling removes all the issues of resource clashing because you can be sure no other task can run until you pause. So I've still got people watching me, so that's good. Yeah, right. So Forth is wonderful. Now for some of the ideas used in my code. The Forth I use is 32 bits wide. The ADCs are 12-bit. The PWMs are usually 10 bits wide as a good trade-off between speed and resolution. So my inputs are from ADCs and odometry counts. They're all fixed point and not very many bits, no more than about 16. My outputs are PWM numbers to control the motors, and for those 10 bits is sufficient. All my arithmetic is in 32 bits. So there's absolutely no need for floating point. So I don't. Lots of mouse builders do though, and they get mixed results. I can't hear very loud things. Is somebody talking to me? Hello? Okay, I'll carry on. I use mouse units for my calculations. So I use odometry counts instead of millimeters. I use counts per second instead of meters per second. I use sensor readings, sometimes linearized, instead of millimeters again. I have words to convert these mouse units into real units for when I want to interact with the mouse. So I might interact in millimeters and I don't know, whatever. But the mouse internally works in mouse units. So that's similar to the way that Forth does all the internal operations in binary and only converts to decimal when interacting with the user. I don't want any overhead in my control loops, however user-friendly it makes the code. Thing that comes up all the time, over and over again, is switching between mouse relative and maze relative coordinates. Okay. So for example, the mouse's left wall, the wall on the left side of the mouse, might correspond to a north wall, an east wall, etc. in the actual maze, depending on which way the mouse is pointing. So I use the mouse direction as a pointer to a table of execution vectors to do the conversion. There's no case statement, no nested if. It's rock solid, consistent execution times. I find execution vectors in Forth easy, probably because the syntax doesn't get in the way and I can make it easy to read without confusion between symbols. Now, a few years back, one of my teenage groups here, I was teaching them Forth, and one of the chaps got so carried away with execution vectors, he was using them for absolutely everything, and eventually had to be turned back a bit and occasionally use an if. The control algorithms are simple PD controllers, that's proportional differential. There's no integral term. The I term normally takes out systematic errors, such as different wheel diameters, that kind of thing. It's much better to build the thing properly in the first place, and it also gives a faster response.
What are execution vectors?
Okay, I'll stop sharing and talk. Okay, well, in Forth, and many other languages, I suppose, you can have a function and you can have a pointer to a function. Now in Forth, we generate the address of the function by using tick, the little apostrophe thing. So tick Fred will return the execution address for Fred. And tick Fred execute. So you calculate the vector for Fred and then execute it. So that will be exactly the same as typing Fred in the first place. But if I've got 4 things to do, let's call them north, east, south, west, okay? They could be anything. Check the wall, set the wall, whatever they are, right? So I can take here the address in the dictionary. I can then tick north, comma, tick east, comma, tick south, comma, tick west, comma, and then constant vector table. Okay? So I'll have 4 consecutive addresses in memory which contain 4 different execution vectors. So I can now look up in that table using my mouse direction number, which is in the range 0 to 4. Probably going to have to do some messing around, get the cell sizes right and all that kind of thing. But I look up in this table which one of these I want to execute. So it's vector table, puts the address of the first one on the stack. Mouse direction fetch, which will give me the direction the mouse is pointing. Plus, which will add that offset to the base address of the table. Fetch, which will fetch that execution address onto the stack, and then execute, which will do it. Okay? So if the mouse is pointing north, my direction number will be 0, and I'll do this one. If my mouse is pointing east, my mouse direction will be 1, and I'll do this one. Okay? But because these, in principle, should take the same time to execute because they're doing very similar things in different directions, the execution time is the same whichever one of these I do. Whereas if I use a case statement, so if I used the mouse direction fetch case of, that would actually be implemented as a load of nested ifs, and it would take longer to execute this one than this one. Does that all make sense?
Yes, it does. No speculative if branching and stuff like that. Yeah, no.
Right. Okay. Everybody happy? I'll carry on. I've got an awful lot to get through. Sorry. Okay. So proportional and differential, the values of those is found by experiment. Basically, you turn this bit up until it wobbles and then turn this bit up until it doesn't wobble and keep doing that until you crash. There's a whole load of non-linear stuff goes on, which makes it difficult. So when you're really accelerating fast, so that the wheels are at the slip point, increasing power on the left wheel will increase the slip, reduce the acceleration on that side and cause the mouse to turn left. That's the opposite of the situation at low accelerations. Going fast is hard. Control is the really hard part. If you can make your mouse accelerate or brake hard in a straight line to an accurate position and turn through a controllable angle to a controllable position, you've done the hard part. Now for the easy part, solving. So I think of the maze as a 16 by 16 array of information. The start cell is at the bottom left corner. Directions are referred to by compass points. So in general, the mouse will have cells to the north. Not sure I can get this the right way around for you. North, east, south, and west of its current position. And positions are defined by a northing and an easting on the stack in that order. The double number operators are quite useful for these. I take care to hold each piece of information in only one place. So the north wall of a cell is also the south wall of the adjacent cell. If you hold them separately, you could end up if you've got something wrong in your software with the south wall of this cell being present, but the north cell of the cell below it being absent, and that can cause chaos. It's very easy. You can see the sample I put up there where the code for north wall is just go north and look at the south wall, etc. So I only hold west and south walls, but I have to use a 17 by 17 array to allow for extra cells around the edge that hold these south and west walls. On previous mice, I've packed flags into bytes and unpacked them for use. This enables a single byte array for all the mouse data. It works, it's fine. It's what I'll be showing you in a minute. But I realized recently that the chips we're using have got what I would think of as acres of RAM. They've got 16 kilobytes of RAM. And so I now have a byte for each flag. And all I have to do is cfetch and cstore instead of all that masking and writing back and so on. So I've got 5 flags per cell. So as well as the wall data, I need to know if the mouse has visited the cell. Because if it's visited the cell, the walls are correct. If it hasn't visited the cell, in general, the walls aren't there. The solved flag is used to prevent a cell going through the solving process more than once. Come back to that in a bit. The found flag propagates through the solving process to show that the cell has a known fastest route to the target cell. I use 2 sets of maze data, at least for the walls. The virtual data contains a downloaded maze. So I've got mazes that have run in previous competitions and that kind of thing. I can download one of those into the virtual maze. And then as the mouse moves around what it thinks of as the real maze, it can copy information from the virtual maze for the simulator and put that into its own maze for the walls that it would have found if it was running in an actual maze. But by having the 2 sets of data, I can choose which one I'm looking at with a pointer. I switch backwards and forwards. So all of my database words can either be working on the virtual maze or the, in quotes, real maze. So I can download mazes to test the algorithm. So that's another nice feature of Forth type things using pointers. So now life gets a bit complicated because I'm sure you're all bored with looking at this this PowerPoint stuff and me rabbiting on about it. So I'm going to see if I can change to looking at the data from some real code and have me rabbiting on about that instead. Everybody happy so far? When I'm back talking, can see everybody's faces. Okay, I've taken up a lot of time and I've got a lot more to do. I'm sorry.
You're fine. I would suggest that if you're going to go more than 20 minutes more, maybe consider making a part 2. How do you feel about that?
Well, I'll shrink it as fast as I can. One of the problems that I've got is that my maze simulator, this thing that's just come up on the screen, suffers from being quite slow because it has to do a lot of writing over a serial link to a VT100 terminal. And if I speed it up a lot, I think Zoom might get confused. So we'll start with it fast. And can somebody tell me if the video is just useless? Okay, so this is running on mouse hardware. I've got a little processor board that I use for this, this kind of thing. It's the real processor board that's used in the real mouse. So the same code is used both for simulation and the real mouse. I only wrote the code once. So any limitations to the hardware become apparent during development. If you're doing your simulation on a PC in Forth or a different language and not actually running it on the real hardware, you can really mess yourself up. You can convince yourself that your software is fast enough when it's nowhere near fast enough. So this is a representation of the maze as the mouse thinks it is at the start. on the bottom left-hand corner, you can see a little caret symbol. This is the mouse, and that symbol will change shape depending on which way it's facing. So the mouse is currently facing north. You'll see a little asterisk next to it. That means that that cell has been visited. It's the only one that has been visited. Okay. In the center of the maze, you'll see a T. This is the target cell. This is where the mouse is aiming at. Now, there's 4 cells in the real target, but it doesn't matter, because if you get to one of them, you must have got through the timing gate in the center, which is what you're trying to do. Okay. So here we go with the solving algorithm. The function of the solving algorithm is to tell the mouse what to do when it gets into each new cell. And the way we do it is this. I put the position of the T, the target, into a queue. And then from then on, I keep taking things out of the queue and going around the 4 adjacent cells. And if there's no wall, it checks to see if the maze is in the adjacent cell. And if it is, you move the mouse into the target cell and you finish. That's great. If the mouse isn't in the adjacent cell, it puts that cell into the queue and marks it as solved. So if I just show, with a bit of luck, if this all works, if I just show what happens when I take the first cell out of the queue, you can see I've marked, yep, it has worked. I've marked the 4 cells next to the T with an S, which means they're solved. The mouse doesn't know about any walls in this area at the moment, so that's what it does. And I can keep coming there. You can see I've done it again. So I've taken the cell north of the T, which was the first one in the queue, taken that out of the queue and put 3 new cells in the queue adjacent to that. Okay, and I can keep doing this. Okay, and let's see if I can speed that up a bit. Okay, so I'm going to have to keep pressing space until I get close. On the video, it looks as though it's keeping up fairly well, so that's all right. Sometimes it does. So we're going to work our way pretty much through the entire maze at this position because the mouse is so far away from the target. We've just about reached the maximum queue length here, which is something like 32 queue elements. I always make the queue size vastly too big, just in case my maths doesn't work very well. Okay, you can see we're getting close to the mouse. I'll keep doing this, and eventually the relevant cell has come out of the queue and the mouse has moved 1 cell forwards. It's now going to look at the adjacent walls and put them in if they're in the virtual maze. So if I keep going now, I've reset the queue. I've got some new cells solved and stored in the queue. Okay, so now I can do that whole process a bit quicker. And something has gone horribly wrong. Don't know what. I've now pressed the wrong button, and it is going to do the complete solve of the maze the way the mouse would actually do it. Well, at least it speeds things up. Okay. You can see every now and then the mouse gets stymied and has to go back and look again. And it gets the center. Once it's got to the center, it moves the target back to the start and solves back to the start. Now you'll see some of the cells in the bottom left-hand corner are now green asterisks. And that means they're found. The mouse knows its way back to the start from there. As soon as it reaches a found cell, it goes off searching back towards the the center, because there's no point going all the way back to the start if it already knows the way back to the start. So it searches backwards and forwards between the start and the center until it eventually finds itself on a cell that is on the shortest route from that cell to the center and the shortest route from that cell to the target. At that point, it has to go all the way to the target and then solve back to the start again. That's what it's doing now. And again, once it finds a green cell, it will start solving back to the center. And eventually, it will find itself at the center, but also that the center cell is a found cell that knows its way back to the start. I was going to try and explain this better, but I pressed the capital R button instead of the lowercase r button. So it's gone off and done its thing. Right, it has now found the shortest route. So all the cells back to the start are now green ones, and it's searching back to the start. So it's following the shortest route back to the start. Is that working okay for you lot on the video?
It's fine.
Okay. So now you can see we've searched and all the rest of it. It's done 490 cells, 293 turns, and it thinks it knows the route, but it's not doing what I expected it to do. So let's see what happens. Nope. Let's see what happens. This is the fastest route for this mouse at this time. So what it did on its last route run back from the center to the start, it remembered every movement it had made. So it encoded, I did 5 in a straight line and then I turned left, and then I did 1 in a straight line and turned right, and so on. So it's got that list of actions that it did, and then it replayed those backwards as the fast run. So you can see up the left-hand side, there is a long straight there. And with this method, I would have known how many cells that straight was. So I could do an acceleration profile starting from rest at the start up to peak speed halfway along and then slowing down for the corner. Actually, peak speed would be a bit further than that because I don't have to slow down to rest for the corner, just to the speed at which I can make the corner. So that is the shortest route that this mouse finds. It might not be the fastest route, sadly. The clever mice, cleverer than mine, where the mouse has consecutive turns. So if you look at towards the top left-hand corner, third cell across, the desired course comes down 1, right 1, down 1. If you're clever enough, you can take a diagonal path across those 3, which will be faster than the 90-degree turns that I do at the moment. In a similar way, you might find that a longer, straighter run was faster than a shorter, jiggly run. So these are the kind of optimization you'll have to make once you know enough about the maze. But what I do here is typical of what people do to find the shortest route. So I think what would happen next if this is behaving itself. No, it's not behaving itself. Okay, that's not what I expected to happen. Let's see if lowercase r does what I expected it again. Okay, right. So just checking my notes. I'm going to switch back to the PowerPoint. I'm going to press my button. No, it's not working for me. Done the editor. That's it. The last bit was very quick because I was running out of time. So thanks for listening. I'm going to close this sharing now and ask any questions.
What is the algorithm for determining what the fastest route is?
The algorithm that I use, as you can see, that the queuing method will find the shortest route because it finds the mouse with the least number of queued elements that reach it. Yeah. You start at the top of the queue. If the mouse was next to that, you'd be straight there. If not, you're putting the next element in the queue. So this element that is nearer to the target will go into the queue first compared to an element down here somewhere that went into the queue later. So whichever of those comes out of the queue first next to the mouse will be on the shortest route. Does that make sense?
Clever.
Let me, so the rules are you can explore the maze totally and get a understand its map, and then you optimize the path.
Yeah. The rules are slightly different in the UK and Japan to what they are in America. So in the UK and Japan, you get 10 minutes in the maze, and you're allowed to leave the start cell 5 times. Now in America, I think you still get 10 minutes, but a percentage of your search time, a percentage of the time that you've been in the maze is added to your run time. Okay, so if you spent 10 minutes in the maze finding the fastest route and then run it in 2 seconds, you'll still lose.
It's I actually and I know I talk about doing this when I first learned to compute in 1963 and 64 on a IBM can't add doesn't even try 1620 in Fortran. Martin Gardner had a mathematical games column in Scientific American, which used to be a good magazine, on Bridget, a game called Bridget. And essentially it's maze running where the thing is to find the way out on the other side. So I tried that, and actually I failed in Fortran. Later, around 68 or so at Northwestern, I learned Algol, which had recursion. And so you could store your backup route and so forth. And in Algol, I solved, knowing whether I had gotten through from one side to the other of Bridget, which is essentially a maze running problem. And then in APL, I got it down to like left, right, forward, backwards and so forth for 1-line or 2-line functions and to do it. But of course, you're dealing with a lot more global problem here on solving the fastest, and even considering your accelerations and so forth. But yeah, definitely that's impressive. But I've always and also I should mention that actually I actually was in visual psychophysics, but had to take a course in learning and so forth in psychology. And I wrote a paper, maze running on an IBM, on a CDC 6400, where
we're at left field. Break. Stop, Bob. I think we're out a little bit in left field. We're going to try to stop sideways excursions. Chris has his hand up.
Hi, thank you. Great talk. Really good example of using Forth for real-time control. There are 2 of us here who are very interested in FPGAs. I'm curious which actual chip you're using, and is there anything that an FPGA could help with on these types of real-time control problems?
I'm not using an FPGA.
Right.
The reasons for that are, first of all, I don't really know how to. But secondly, if I did know how to, I'd have to add an extra chip to do it, unless I put a fourth processor on the FPGA and all that kind of thing, which is really beyond my technology. You've got to remember we're constrained in every which way. We need everything to be as lightweight and low power as possible. And we need things like A to D converters and PWMs and so on. Now, the analog stuff is probably difficult to do on an FPGA. And if your solution is going to take more than one chip, it's almost invariably going to weigh more and cost more. So as long as we can do everything in one chip, that's what we'll probably do. But having said that, an FPGA would make some of the things a lot easier.
Such as?
Well, for start, your control algorithm would run virtually instantaneously. I don't think the solving algorithm would necessarily run any faster if you use the sort of solving algorithm that I use. I guess you could write a processor for each cell in the maze and have them sort of talk to one another over very fast, some kind of comms thing. But that's going to be quite a challenge to do. You know, there's a lot of VHDL to write to make that happen, I think. There'd be an awful lot of these processors. You need 256 of them. And power is an issue. We've got to be able to run for 10 minutes on, if we're trying to be competitive in half size solving, on something like a 100 milliampere hour battery, and still be able to take 1 amp peaks out of that for the motors. So FPGAs, as I understand it, are very fast and probably power efficient, but because they're doing so much processing, so much work, the current draw from the battery is quite high.
And which chip are you using?
I'm using an STM32F072.
Okay.
It's a 48 megahertz M0 plus. One of the reasons I like it is the A to D converters are really fast. I think they're 2.5 microseconds, 12-bit A to D converters. That's really nice. And it's sort of fast enough, you know. I mean, people used to do this on 6502s.
Mm-hmm.
But I can see the attraction of doing it on an FPGA. It would be a clever way of doing it.
You're right about the power consumption would be higher. I will actually, we exchanged emails in August of 2023. I will dig around to see if there are FPGAs with the I/O ports and how big the chip actually is. And I'll send you an email and, maybe we'll follow this up a little bit. You can actually get fourths. Microspice is a fourth that runs on FPGAs. You can either run multiple fourths on an FPGA, or what you can do is you can do like a barrel processor where a single core rotates between multiple tasks. So anyhow, excellent talk. Thank you.
You're welcome.
What is your fastest time through a maze that you personally have done?
I'm absolutely dreadful at solving. To give you some idea of my personal motivation, back in the 90s, when I first came across Micromouse, I was trying to encourage the people that ran it to get kids involved, because for me, and then part of an engineer's responsibility is to generate the next lot of engineers that are going to take over from him. Right? So that was when the UK line following started, because line following is a lot easier for the kids. And I had my son doing line following, and he was champion and all the rest of it. He was very good at it. And then I had other kids doing it. And the process that I go through with each group is we start off on line following, because that's easy and there's nothing to crash into and you can get satisfaction out of it. And then we move on to wall following, which puts you into the maze and you find all the nasty things about trying to get around these corners. Now, each of these takes about a year, and in the third year we get into solving. Now my current group are just in that position. We got into that position last when COVID hit, and stop the whole lot. So I don't actually get very much time to make solvers, and my solvers are dreadful. For me, getting to the center of the maze is a massive achievement. And for most solvers, getting to the center of the maze is a massive achievement. You get a medal for course completed if you get to the center of the maze. And as long as it takes you less than 10 minutes, you've achieved something. And I count myself lucky when I get to the center of the maze. I never get as far as doing a fast run.
It's not how well the bear dances. It's just that he dances at all.
Absolutely.
I'd like to, at this time, award you the Bill Ragsdale Prize for really great presentation.
Thank you.
Thank you so much. I'm encouraged to ask you, are you willing to come back and take little side trips into various pieces of your domain? I'm interested in how you talk to the Bluetooth on a little processor, embedded processor, especially in the limited constraints that you have. We'll talk via email, but is that something you're willing to do, is come back and talk to us again?
Sadly, I am very overcommitted.
Well, we'd like to thank you for this one. Thank you for fitting us in.
You're very welcome.
And if you have the urge to talk about anything else, we're going to be here, I expect. With that, thanks again.
Just one other thing before I go. I will, if I can work out how to drive this Zoom thing, I will leave some links on the chat. Is there a chat or something on here?
Yes, there's a chat, and you can do that after we've moved on.
Okay,
hopefully you can hang around for another 20 minutes or so and get that done. But now it is time for the monthly screenshot. Turn your camera on unless you're on the lam. If you're on the lam, change your name, turn your camera off, sign off for 10 minutes or 2 minutes. How long could it take? How long could it possibly take? So now's the time, Brad.
All right. I'll give everybody 1 sec more, and then one.
Hang on, my camera's not working anymore.
Uh-oh.
Would you like a webcam, USB webcam?
It is a USB webcam.
I can give you a USB webcam if you feel like you need one.
No, what I need to do is exit out of that because reasons for unknown. Let's see if this works. Yes. Okay. There we go.
It worked.
All right. Everyone on camera that would like to be on camera. Okay. Smile. 1, 2, 3. Okay.
I think this guy iPad is hiding from the law. All right, Bill Ragsdale, who's always ready when it's his time, well prepared with excellent stuff and gets the ball over the plate. Needless to say, it would be redundant to give Bill Ragsdale the Bill Ragsdale Prize, but he's earned it every time. On with the show. Introduce yourself, Bill.
You, Bill.
I see your screen, but I don't hear any audio.